Hi chemists, Mr. Peluso here. Today guys we're going to be covering rates of chemical reaction. So let's get straight into this one. Just a brief review of what rate of reaction is actually referring to. It's indicated by the time taken for a specific amount of change. So whether that's mass, concentration or amount in moles in either reactants or products. So we can describe the rate over a period of time, which is referred to as the average rate of reaction, or during a chemical reaction, if we're tracking the amount of substance, we can talk about the rate at a particular instant in time, which is referred to as the instantaneous rate of reaction. So first of all, I've got a rather kind of sloppy rate of reaction graph drawn here. So we've got a chemical reaction which is indicated up here. It's a pretty basic chemical reaction between an acid and a carbonate, and one of the products is carbon dioxide gas. Now the carbon dioxide gas is going to be up this tube here due to its low density obviously, and it's going to be filling up this syringe system. So the syringe is going to expand based on the volume of gas that's in there, and that's going to be recorded. And by doing that we can plot a very rough graph here, but the shape is what we're really looking at. So the y-axis, we've got the volume of gas produced in centimeters cubed, and we've got the time. Okay. Now when you add the reactants together, first of all you're going to have the rate of reaction being quite high. So rate of reaction is the volume divided by the time. So we can see that the slope of the graph initially is quite steep. Okay. This is because the reaction of the the concentration of the reactants is at their highest. So we've got lots of reactant particles combining, and the reaction is going to completion quite quickly. So initially you've got a relatively quick amount of that gas being formed. But as the reaction continues on, there's the reactant particles that have converted to product particles. Now there's less reactant particles. So the rate of reaction is going to be slower and slower, which is being indicated by the fact that the curve of this graph is becoming less steep. So the slope is decreasing here, and it's getting less and less and less steep until it eventually becomes rather flat. When the reaction's gone to completion, the slope of the graph will be zero, so it will be completely flat. So at this very stage, this stage here, which is probably near the end of the reaction, it's really flattening out here. So this is the kind of shape that we're looking for. So in this instance, the rate of reaction is being defined as the change in concentration divided by the change in time. Okay, so you're going to have to pick 2 points of this graph in regards to a slope, and you're going to have to say, okay, how has the concentration changed and how has the time changed in those 2 points? So here's a more simple graph. So we've just got the same kind of curve. So we've got a steep slope at the beginning, and then it's flattening out as the reaction goes to completion. So here we've got a change in mass, or a loss in mass of grams, and we've got a time in minutes. So what's the general trend of this graph? What is this graph showing us? Have a think. So we're saying initially the slope of the graph increases, indicating an increase in the rate of reaction. So that's because the slope is quite steep at the beginning here. The plateau in the graph indicates that the reaction has stopped. So plateau means that slope of zero. So the reaction's gone to completion. Now you might have to figure out the slope of a graph like this. So the instantaneous rate of reaction at 2 minutes. So 2 minutes is indicated by this point here. Alright, so what we'd want to do is use a ruler. So this is the point that we're going for here, because this kind of lines up. Okay, I'm just going to do it very sloppily. That's bad. But that's basically what we're going for here. To get the instantaneous rate of reaction, what we want to do is basically create a tangent. Okay, so it's the 2 points of this graph. Now the way that the shape of this graph looks, a tangent to this point is basically where the graph is going to go anyway. So my 2 points might be here, and we use the origin 0, 0. So the formula is y2 take y1 over x2 take x1. Okay, so reading off this point here, now mine's quite sloppy, but it looks like to be 25. So if I'm doing my formula, y1 over x2 take x1. So that's my slope formula, okay? So my second point here, so my coordinate here, my x coordinate is 2, and my y coordinate is 25. And my origin down here is 0 and 0. So my y2 point would be 25, take 0, which is my y1, divided by 2 over 0. So if you divide those two, you're going to get 12.5. Okay, we won't worry about units right now, but we'd say 12.5 is our instantaneous rate of reaction. So basically we're doing change in mass over change in time. So that's being considered our rate. What would you do for the average rate of reaction for 5 minutes? Now, instantaneous rate of reaction means that you have to do a tangent. So if I was doing the instantaneous rate of reaction at 4 minutes, the tangent to the line would look something like that. And I'd be getting 2 points from that tangent. But if I'm going from 5, that's approximately here, and I'm talking about the average rate of reaction, I have to start from the beginning. So I have to take into account any 2 points on this line. So not a tangent, you could literally pick any 2 points on that line. The easiest 2 points for average rate of reaction would be that point right there, because you need to take that 5 into account. So this point has coordinates, if I'm going across here, I'd say about 38 or 39, and the x is 5. So I'll go 5 and 38. You'd obviously be more accurate with a ruler. And the other point, you could again take the origin of 0 and 0. Okay? So if I'm using this same formula, and I'll just do it over here, my y2 point would be 38, subtract 0, divided by this point here. And you would do that division. Now, I don't know exactly what that is, but 40 divided by 5 is 8, so it's going to be around about 8. So it's just less than 8, so it might be approximately 7.9. Okay, so my answer of 7.9 is actually much less than this instantaneous rate here, which makes sense, because at this point, the slope of the curve was much steeper compared to this point here. Okay, you have to average out that entire section. So basically the slope you'd be looking at, my pen's really bad, is something like this, which is much less steep, which kind of confirms that slower rate of reaction in that case. So the next part in terms of rate of reaction is referring to collision theory. So collision theory is the fact that in order for particles to change, they need to actually collide with each other. So they need to physically hit each other. And that's what we've learnt in the past. So there are 2 types of collisions. We can have productive collisions, which are collisions that form product, or we have non-productive collisions. And in that case, there's no product forms. So they basically just bounce off each other and the reactant particles stay the same. In order to define between productive and non-productive collisions, the colliding particles must have sufficient kinetic energy. Okay? Now, the kinetic energy that's required in order for particles to form product is called the activation energy, which is symbolized by this EA. So the rate of reaction in terms of collision theory is dependent on 4 factors: the size of the activation energy, the frequency of collisions, the energy of particles, and the orientation of particles. So activation energy, we refer back to our diagrams that we looked at previously in terms of energy profile. Okay, so these graphs here refer to exothermic and endothermic reactions. Exothermic reactions mean the total energy of reactants is greater than the energy of products, so energy is released into the surroundings, that excess energy. But the part of this graph that we're looking at here is this part, which is the activation energy. Okay, so initially the reactant particles are down here. Now, in order for those reactant particles to form product particles, they need to increase their level of energy to this part here. So this peak is what's called the activation energy. So the difference here between the energy of reactants and the activation energy is indicated by this arrow here. So those 2 colliding particles need to meet that activation energy in order to form products, and then that excess energy is going to be released. You can see for an endothermic reaction here, where the total energy of reactants and products is essentially switched, the activation energy still needs to be reached. And you can see that that jump is much higher, and that's because energy is required from the surroundings in an endothermic reaction. So we need to absorb some energy from the surroundings in order for that reaction to go to completion. So in either exothermic or endothermic reactions, the particles need to still reach that activation energy, which is higher than anything that's achieved so far. Energy is used to break bonds within particles, and that energy comes from the kinetic energy of the colliding particles. So basically what we need to do is those colliding particles combine their kinetic energies. So they need to be hitting each other with pace. So if the combined kinetic energy of any two colliding particles is greater than the activation energy, you've got a productive collision and the reaction may take place. If the combined energy is lower than the activation energy, then no reaction will occur and the reactant particles will just bounce off each other. So the particles need to reach that activation energy. But there's another factor as well. It's not just energy that needs to be overcome. For a successful collision to take place, where reactant particles form product particles, the particles also must be orientated correctly. So this is kind of like those kind of little shape games where you're putting the shape inside the correct sized hole. You need correct particle orientation. In this case, we've got our two reactant particles here, and you can see that the shape is kind of perfect, okay? So when they collide in that orientation, they're going to form product. So it's going to be a productive collision, and you're going to produce something different. In this case, that's kind of visualized by these two reactants just kind of combining. So maybe they're forming a new chemical bond, okay? And this could be a new molecule. Incorrect particle orientation is pretty self-explanatory. If those two same reactant particles collide, and they may have enough activation energy, but it's the wrong orientation, they'll just bounce off each other. So you can see here that this shape doesn't quite fit together, so they're going to fly off again and look for a new collision to occur.